Okay, kids, Thermo Chem homework number 2. Put your name there. The law of conservation of energy. Energy cannot be created or destroyed in a chemical reaction or physical change, dash, it can be transferred. Specific heat capacity, the amount of energy required to raise or lower the temperature of 1 gram of a substance by 1 degree centigrade or 1 Kelvin, which is the same amount of energy. For example, if you have 1 gram of water at 14.5 centigrade, the amount of energy required to make it 15.5 centigrade to raise that temperature of 1 gram by 1 degree would take what's called the specific heat capacity constant. For water, that happens to be 4.18 joules per gram dot Kelvin. We use Kelvin, but it could be centigrade as well. Okay, 4.18 joules per gram dot Kelvin. That's a pretty high number. For copper, just so you get a handle on it, copper's is 0.39 joules per gram dot Kelvin. It takes much less energy, 0.39 joules, to make copper raise its temperature 1 gram by 1 Kelvin. Water is actually much, much higher. And that's very obvious. If you ever had a copper pot, or you could imagine a copper pot, some people actually have copper pots to cook in. Those pots happen to be a little more expensive than the regular pots. I don't happen to have one in my house, but it's a metal pot. Metals have lower specific heat capacity constant. If you put some water in a pot to set it up to boil, you're going to make macaroni and cheese, and you put the stove on high for a minute. Then you change your mind because somebody comes home with the pizza pie. You turn the water off. In 1 minute, the water didn't get very hot, but the bottom of the pot that was near the fire is very, very hot. I got to turn this commercial off. I was listening to some music. I had some Mozart on, and now some silly commercial came on. So different substances will heat up faster or slower. Depends upon 2 things: what they're made of, because they have a specific heat capacity constant. Also, how many grams are they? It's easier to heat up a small pot of water than a big pot of water, because in order to get to the boiling point, every gram of that water has to be raised up by 4.18 joules. So if you have a lot of water, you got to add a lot of energy to get all of it up to the boiling point. All right, let's see what we got going on here. How many kilojoules? Now this is different. This is kilojoules, not joules, to vaporize 311 grams of water. Now, the formula Q equals mH of V is going to help us figure out how many joules, Q, will it take to vaporize that. So this is going to be Q equals 311 grams times 2260 joules per gram. This constant, the heat of vaporization constant, is the amount of energy required to make 1 gram of a substance go from the liquid to the gas phase. For water, that's the number, and it's on table B. Now, to do this problem, we're going to multiply 311 times 2260, and the number comes out, Q equals 702,860 joules, but we can only have 3 significant figures, so Q is equal to 703,000 joules. but this is joules, and the question says kilojoules. So the next thing we have to do is this, 703,000 joules over 1 times there's 1,000 joules in 1 kilojoule. How did I know that? Because the number kilojoule means 1,000 of the little ones. This is going to equal 703 kJ. That's the answer for that. For this next question, number 3, which I've always really liked, because I like olive oil, 870 point joules of heat is added to just 6.8 grams of olive oil at this temperature, 294 Kelvin. And then you put it in the frying pan, you put it on the stove, and the oil temperature goes up to 358 kilograms. 358 Kelvin. Holy smokes, I'm tired. What is the specific heat capacity constant of olive oil? Ooh, this is tricky business, right? How the heck are we going to figure this out? Well, we have a formula, Q equals mc delta T. And what this means is Q, which is the heat energy in joules, is equal to the mass, in this case it's going to be the mass of olive oil, times a constant called the specific heat capacity constant. For water, let's roll back. For water, the C value is 4.18 joules per gram per Kelvin. For copper, it's only 0.39 joules per gram dot Kelvin. For olive oil, it's the unknown. We're going to figure that out. Now, triangle T, delta T. Triangle means delta. It's a Greek capital letter called delta, and it means change in temperature. The temperature goes from this number all the way up to that number. What's the difference between those numbers? That's what delta T is. So, how much heat did it take? 870 joules. 870 point joules with 3 significant figures. The mass, 6.8 grams. That's only 2 significant figures. Times C, that's our unknown. We don't know what that is. Times the delta T, 358, take away 294. The difference between this, look, I'm showing you how to do math. I haven't done this. 64.0 Kelvin with 3 significant figures, but we need only 2 significant figures in our answer because of this number. Now we got this number here and we got these numbers here. We got to get the C by itself. So we're going to divide both sides by 6.8 grams times 64.0 Kelvin. And we're going to divide this side by 6.8 grams times 64.0 Kelvin. Now, it's a little messy. This cancels, and this cancels. So we have C by itself equal to all of this. So I'm going to move this way so we have some room. The answer is going to have these units, joules on the top, divided by grams times Kelvin, which is the unit that we want. Now to do this math problem, let me get this calculator going so you can see it. We're going to have clear 870 divided by 6.8 divided by 64.0 equals, that's not going to work. I don't like that number. Let's do it this way. 6.8 times 64. We'll write this number down. It's going to equal, can you see this number? It's going to equal 870 divided by 435.2. I multiplied the bottom 2 numbers to get this, and we still have to divide. So it's going to be 870 divided by 435.2. And there's a number I really like, 1.999908. With 2 significant figures, I'm going to have to squeeze this. I don't know how you're going to see this. C equals 2.0 joules per gram dot Kelvin. That's the answer. Now, what does that mean? That means if your name is olive oil, how much energy does it take to change your temperature? It takes 2 joules of energy to make every gram of olive oil change temperature by 1 Kelvin. Now, the change in temperature in Kelvin is the same as the change in temperature in centigrade. So K and C in this case there, because it's a delta T, it's interchangeable. Next question. Let's fold this back so we have a little more control over what's going to show up here. Let's see what we got going on. How much heat's required to raise the temperature of a pound? Now, a pound is, we'll just cross that out, 454 grams of mercury. We're going to go from this temperature, that's going to be the delta T. If the specific heat capacity of mercury is this tiny number, mercury changes temperature very easily. It takes very little number of joules to make every gram of mercury go up by that. So the question now is how much heat in joules? So to do this, we have to write this formula. Q equals mc delta T. The Q is the unknown. We don't know how much energy it is. The mass is 454 grams. What the heck is C? That's C right there. 0.140 joules per gram dot Kelvin. It takes that much energy to make every gram of mercury change temperature by 1 Kelvin. Now the delta T, we need to figure out the delta T. 323 minus 293, that'll be a 0. That's a 12 now, minus 9 is 3. So it's going to be 30.0 Kelvin with 3 significant figures. The Q is going to equal, let's get these numbers going here in the calculator, 454 times 0.140 times 30.0, and it's equal to 1906.8. And then we have to say how many significant figures. It looks like 3, so it's going to be 1910. And what is the unit? Well, the grams cancel the grams, and the Kelvin cancels the Kelvin. So it's going to come out in joules, which makes sense because the question says how much heat energy in joules is required. That many joules is required. So in order to make a pound of mercury change temperature by 30 Kelvin, it takes that much energy. Look at this question. How much energy in joules does it take to make 1 pound of water change? Look, the same temperature change. This is going to be Q equals mc delta T. In this case, we're going to compare mercury with water. We have 1 pound of mercury up top, and now we're going to do 1 pound of water. How much energy will it take to make a pound of water change by the same temperature? Well, Q equals 454 grams times 4.18 joules per gram dot Kelvin. How did I know that? That's on table B. That's the specific heat capacity constant for water. And the delta T is still 30.0 Kelvin because these numbers are the same as those numbers. We change the same temperature. And when we multiply, we're going to have 454 times 4.18 times 30.0. Look at that number. 56931.6, and with 3 significant figures, it's going to be 56900 joules. Can you see that? Almost. Let me move this a little so you can see it a little better. A pound of mercury, it takes only that much energy to make the temperature change by 30 Kelvin. A pound of water takes a huge number of joules of energy to make that change by 30 Kelvin. Water has a very, very high C value, specific heat capacity constant. It's very hard to change the temperature of water. It's very hard to make it warmer. It's also very hard to make it colder, right? Because the same amount of energy has to be removed to make it colder. That's why if you have a swimming pool in Vestal, if you don't have a heater on it, the pool water stays pretty cold. Even though the air temperature can get really hot, it takes a lot of energy to warm up all that water in the pool. If you had a little tiny pool like the size of a tablespoon, if that was the size of your pool, it'd be pretty easy to warm it up because there's so few grams, it would take so little energy to warm that up. But if you have a big swimming pool, the sun is not really going to be able to make it quite as warm as a heater. Different substances have different specific heat capacity constants. That means it's easier or harder to warm them up or to cool them down. One day, years ago, I was having a pool party with my daughter, and I left the heater on overnight, and it didn't have a thermostat. That old heater was just on and off, and I left it on all night. And the swimming pool got to be literally about 97 degrees Fahrenheit. This is the Fahrenheit thermometer. Instead of having it about 90, it was about 97. It was literally too hot. So on a hot day, instead of being refreshing, the pool was too cold. I had to just run the hose with cold water in all day to try to warm. It wouldn't cool down. It was so hot, but it held its temperature. Water's specific heat capacity constant is very, very high, and that gives water a lot of its properties that are good. And if you're dumb and you leave the heater on all night, it can be a pain in the neck. There you go.